So in this video I'm going to be talking about types of decay and types of interaction and using different ways to illustrate the interactions that particles undergo. So the first thing we need to look at is actually some conservation laws. So looking at other parts of physics, you probably have come across some of these already. So you might well, from electricity here for instance, know about conservation of charge. From GCSE you'll know that energy has to be conserved, and those of you doing mechanics might know about momentum and how it has to be conserved as well. In particle physics, those all have to be conserved still as well, because they must always be conserved, but there's some other properties that must also be conserved. They are baryon number, electron lepton number, muon lepton number, and tau lepton number. And I'll explain those in a little bit more detail in the next slide. So the way we apply these, so let's say we have a equation of interaction. So particle A is interacting with particle B, and what they're doing is forming particle C and particle D. Now if we're applying the conservation laws, say we're applying conservation of charge, the total charge on this side before the interaction must be equal to the total charge after the interaction. So let's say A had a charge of +1 and B has a charge of 0 and then C has a charge of 0. In order to be conserved, that must mean that D has a charge of +1, so the total charge on both sides is the same, so it's been conserved. Okay, so let's dig into these properties in a little bit more detail. So let's first look at baryon number. So if something is a baryon, it has a baryon number of +1. So like a proton or a neutron, they both have baryon number +1. If you're an antibaryon, so you're an antiparticle, that would mean you have a baryon number of -1, so antiprotons, antineutrons, or anti-anything else. If you're not a baryon, so you're a meson, you're a lepton, anything else, you have a baryon number of 0, so they have no baryon number because they're not one. The same thing works for the other properties as well. So if we look at electron lepton number, if you are an electron type lepton, you have +1. If you're an anti-electron type lepton, you have -1. So like a positron is the antiparticle of an electron. So it's an electron type, but it's an antiparticle, so it has -1. So anything that isn't an electron type lepton has a number of 0. So like a muon has a 0 because it's not an electron type lepton. Okay. And those rules will apply for the muon and tau conservation as well. There's a bit of an oddball in here, is strangeness number. Now, this strangeness is a property of things, so things either have strangeness or they don't, so it is kind of like charge. But we only need to worry about conserving strangeness if there's a strong interaction involved. So if you have two hadrons on the left hand side of your equation, you know it's going to be strong interaction, and in that case strangeness would have to be conserved, otherwise it doesn't. So if you have a strange quark, you have a strangeness of -1, and if you have an anti-strange quark, you have a strangeness of +1. Anything else, strangeness number 0, same as the other things. So let's actually show some of the conservations and show the appropriate method for showing conservation. So for instance, we have this equation here, which could be one of two things. This is either an electron capture or it might be an electron-proton collision, but let's not worry about that for now. So let's demonstrate that some various properties have been conserved. So let's start with try charge. Okay, so the first thing we need to do is write the number of that property for each particle below it. So if we look here, a proton has a charge of +1, an electron has a charge of -1, that's into a neutron, which is a charge of 0, and a electron neutrino, which has a charge of 0. So then the next line, you sum both sides, so -1 plus 1 begins you 0, and then the total of 0, 0 is 0. So the last stage is actually going, we've got charge conserved because it's the same on both sides. Seeing as that's what you were trying to show, you should always have some reference to that. Okay, so that's this procedure for doing it. You write out your equation, you write the numbers below each particle, so each one is clearly linked to it, sum them like this, and then you can say whether or not it's been conserved, and it's exactly the same for each of the different properties. Okay, so that's conservation laws. Now, you're going to come across a large number of different decays and interactions in the particle physics part of the course. And the important thing is to understand how they work. So we learned in the previous video that actually not all particles can interact through the weak force, only fermions can. But all particles can decay through the weak force. Now, what does decay mean? It's a process of going from an unstable system to a more stable one. And so you may have heard of radioactive decay before. That's exactly what's happening there. These ones are going to be slightly different. A general rule of thumb that you'll find useful with these questions, though, is that if you're more massive, you are more unstable. So the bigger particles tend to decay into the smaller ones. Okay, so that's that. And remembering, whenever you're trying to write a decay equation or an interaction equation, they must obey the conservation rules we've done already, and it's one useful way of working out what the particles are. So let's try and write a decay equation for beta plus decay. Now, some useful facts you need to know in terms of deducing this. First one, if it's beta plus decay, it means a positron has been produced. That's why it's called beta plus decay. And the other key thing to remember is the starting point for beta plus decay is a proton. So on the left-hand side of your equation, your starting point is a proton, and a proton only, because it's decaying. And we know that on this side, we're going to produce a positron. But we're also going to need some other particles to ensure the conservation laws have been followed. And we're actually going to need two more, here and here. So first of all, let's look at baryon number. So proton has baryon number 1. So far on this side, we've got baryon number of 0 because we haven't got any baryon. So what we need to do, let's put a baryon in. Now, a proton's not going to decay into itself. That doesn't make any sense. So the only other baryon you know about that you can be using is a neutron. Okay, so we've got one of the particles we need. Let's look at charge. So we've got +1 here, 0, +1. So currently charge is conserved, which means whatever we've got here must be neutral, otherwise that would stop that happening. If we look at electron-lepton number, we've got 0 on this side, we've got 0, -1, something. So whatever this is, it must make the total on this side 0 because it's 0 here. So what we need is a particle, because this is an antiparticle, and it needs to be an electron type. So, and it needs to be neutral, so it must be a neutrino. It must be an electron type, but it's not an antineutrino because otherwise it would make it -2 and 0. Right. So what we've done is we've used the conservation laws to actually generate an equation for beta plus decay, which is always nice. Incidentally, those of you interested in what's going on with the quarks at this stage, so if we remember, a proton is up, up, down, and a neutron is up, down, down. And then you've got these other particles which are made of quarks. And that's what decay is. Decay is the changing of quarks from one type to another. So you can see this up quark here has changed into a down quark. And that's something that the weak interaction can do. It can cause the quarks to change type. Okay, so that's those. So we've got our equation there. So let's have a look at a way we use to represent different kinds of interaction decays, and they're called Feynman diagrams because they were invented by Richard Feynman. And you need to make the distinction between whether you're showing an interaction or whether you're showing a decay because they're different. So let's have a look at the interactions first of all. So here's a couple of examples. So this is actually showing you strong interaction between a proton and a neutron. So strong interaction doesn't cause the particles to change. So as you can see here, you've got the same particles going in as you do going out. But what you do see is this wiggly line here is called an interaction line, and it's showing the interaction between a proton and a neutron. And this here is known as an exchange particle or a gauge boson, and the different interactions have different gauge bosons. Okay, so this is the strong nuclear force with a pion. This is the electromagnetic force, because these two particles are both charged, and this is your virtual photon. But I'll go into gauge bosons and interaction particles a bit later on in this video. We won't focus on that too much for now. Key thing to notice is on the diagrams you need to show which way time's going. So this is before and this is after. And with interactions, this wiggly line should be horizontal, so it should be perpendicular to your time axis, showing that it's happening instantly. Okay, so that's that. So let's have a look at some of the other kinds of interaction, or more specifically looking at decays. So, as always, your starting point to show your time axis. So, with beta plus decay, what we've got, as we established earlier, is a proton going in, and what you have is coming out is a neutron. Now at this point is where we need to show the interaction line, and because decays take time, the interaction line should be angled up like this. Now out of here should come your positron and also your electron neutrino. So, and coming across here, the gauge boson, or your exchange particle in here, would be your a W plus type, and I'll explain how we get to those a bit later on. Let's just stick with knowing what they are for now. So in terms of beta minus, again, we start with a time axis. With beta minus, instead of a proton going in, you have a neutron, and you have a proton coming out. This time you have a W minus particle. Again, we'll get to that later when it's going on. So it's beta minus, so you have an electron emitted, which means you have an anti-electron neutrino being emitted also. Now, the reason we can determine the charge of these particles here is all about conservation of charge. So you see, this is a junction, so like with the circuits with junctions, this is a particle junction. Going into the junction, you have +1. Coming out, you have currently 0. So then this must be plus in order to conserve charge. And it's the same thing here. Going into this junction, 0. Coming out is currently +1. So this is minus to conserve the charge. And charge is always conserved throughout these diagrams. So it's a useful check to make sure you've done it right. So those are two of the simple decays. Let's have a look at some more complicated decays. So electron capture, got our time axis there. So an electron is captured by a proton using the weak interaction. So you have your proton going in, and you have your electron going in. We've got your exchange boson being showed there. Got your neutron coming out, and you've got your electron neutrino going there. So in terms of working out what the charge of your exchange particle is here, going in to this junction here is +1, currently it's coming out as 0, so it must be a W plus. Now, with captures and collisions, you need to show what's called an action line. So you need to show what is doing what to which. So in a capture, the proton is capturing the electron. So the action line goes from the proton to the electron, and it just looks like this, and you'll see them on diagrams. So that's just showing it's the proton capturing the electron. Because with an electron-proton collision, you have exactly the same particles involved, but this way, because the electron is colliding with the proton, this time the action line is going the opposite way. So you end up with a different exchange particle here, but you end up with the same resulting particles coming out. And then, of course, as always, showing your time. So because the electron is colliding with the proton, and we always say the smaller one's colliding with the bigger one, so the electron is colliding with the proton, so the action line goes that way on your diagram, whereas this one, the proton's capturing the electron, so your action line goes that way, and actually the whole interaction line changes direction because of that, which is why your exchange particle is different in those cases. So that's those ones. Let's have a look at another couple of examples that you need to know about. So a neutron-neutrino collision. So going in, you've got a neutron, and going in this side, let's have an electron type neutrino. Now remember, it's a collision, so the smaller one collides with the bigger one, so neutrinos are tiny, so your interaction line is going to go that way, and coming out, so your neutron is going to decay into a proton, and you're going to have your electron coming out here, so we conserve charge. So in terms of thinking about the charge here, it's going to be a W plus acting that way, because we have 0 going in here, so we have -1 coming out, so this one must be +1, so they cancel each other out. So that's that way. And if we want a proton neutrino collision, proton is going to turn into a neutron. You're still going to have your neutrino going in there. And you need a +1 here to conserve charge, so this must be a positron being produced. Again, it's a collision, so it would have to be angled up this way, and therefore it would be a W minus particle. Again, the action line going that way, again, always showing your time axis there. Okay, so those are possibly the 6 key Feynman diagrams that you're going to need to know, plus the ones for the different types of interaction. So those are some of the critical things you're going to need to know about constructing these. So let's talk a little bit more detail about the exchange particle. So exchange particles are often called charge carriers or force carriers, and this is because in the diagrams you can see they are effectively carrying the charge to ensure that it's conserved at various points. So when you're doing decays, your charge carriers or your force carriers are going to be one of these W or Z bosons, because those are for the ones for the weak interaction. So you can have a W plus, W minus, or if you find a situation where you need a neutral one, that's the Z0 boson. If you're showing electromagnetic, you're using the virtual photon, and if you're showing the strong force, you'd use a pion, which is sometimes called a gluon. Okay, so those are those. So let's have a look at an example type question you might get. So it said, for beta minus decay, write a decay equation and then draw a Feynman diagram. So in terms of writing a decay equation, it starts off with a neutron decaying, and you've got to end up with an electron because it's a beta minus decay. So to conserve baryon number, a proton must be produced, and then to conserve electron lepton number, an anti-electron neutrino must be produced. So in terms of drawing your diagram, your neutron's going in, proton comes out, you've got your charge carrier here to show your conservation of charge. So this must be a W minus boson because we've got to conserve it. Going this way, and then coming out of it you've got your electron, and you've got your anti-electron neutrino. Think about what we're missing from here. Time axis. It's the thing a lot of people forget. Make sure you include it. Another thing to watch out for make sure you show all of these particles moving forward in time. Sometimes I see diagrams where like the neutrino is going down here and is actually going backwards in time. So be a bit careful with that kind of thing when you're doing these diagrams.